Okay, we're going to talk about some specific examples of geometric sequences, and then we're going to lay out some conditions for convergence of geometric sequences. All right, probably can see a pattern here in our first sequence. How do we get from the first term to the second? Well, we might be able to subtract a certain fraction. This is 3/9. We might be able to subtract 2/9 and get to 1/9. But could we do the same thing to get to the next term? No. So addition and subtraction won't lead us through the terms of this sequence. So this is not arithmetic. It is geometric because to get from one term to the next, we multiply by what we call a ratio. And so to get from the first term to the second, can you see that we would multiply by positive 1/3? And then to go from the second to the third, we'd multiply by 1/3 again, and multiply by 1/3 again. And so this is a geometric sequence with a common ratio. We'll call that R. The common ratio is positive 1/3. And so the nth term of the sequence would be 1/3 to the n. Or I suppose we could call R 1/3 and put the n up this way, and it's the same thing. Okay. Is the second sequence geometric? Well, it's pretty clear that we double the first term to get to the second, and then double the term again, and double. So the common ratio would be 2, and the nth term could be written 2 to the nth. Third example, maybe some ratio like 3 to the 4th. Multiply the first term by 3 to the 4th, and we get 9/16, and so on, and so forth. So R is 3/4. Okay. You can have a negative ratio. So example 4, we have a common ratio of -1/2, and so the signs will alternate. And you might recognize a switch here. This nth term could also be written -1 to the nth times 1/2 to the nth, but we'll use R equals -1/2 in our description here in a minute. There's one constant sequence where R equals 1. So 1 times 1 is 1, and so forth. So that's not a very interesting sequence, but we want to define geometric sequence for any real number R. So let's move to a little more general description of geometric sequences. So we've been talking about common ratio R, so let R be a real number. Then we can decide upon convergence depending on the base R, the common ratio. So this limit of R to the n will be 0 if R was if R in absolute value is less than 1, if the magnitude of R is less than 1. So it could be positive or negative, and we still have convergence. If R is identical to 1, we'll have that constant sequence. We will have convergence, and the limit of the sequence would be 1. And the limit of the sequence just won't exist at all if the common ratio is less than or equal to -1, or if R is greater than 1. Okay. Well, let's look at an example where R is greater than 1. Let's start with 3. 3 times 3, 9 times 3, 27 times 3. And we've got the nth term, 3 to the nth. And that diverges because the terms are growing without bound. Okay. This sequence would be related to the continuous sequence, or the continuous functions, y equals 3 to the x, which would be the growth function that grows without bound. What else do we want to say here? Let's go to this next example where R is less than or equal to -1. Let's say -2. Okay, so -2 times -2, positive 4. Times -2 is -8. Times -2 is 16. We continue on till the nth term. Okay. And the magnitudes of these terms are growing without bound. And so the odd terms are going off to negative infinity. The even terms, as a subsequence, are going off to infinity. So the magnitudes are growing without bound, even though there's these oscillations. We saw the uninteresting example where the terms were constant 1. And then if we return to any of those examples where r is less than 1, we can convince ourselves that the sequence will converge. And so we have 2 of those examples. The first example, r was the absolute value of r was less than 1. So by our theorem, that converges to 0, and we can see that. And even in the fourth example, where r is -1/2, it doesn't matter that the signs of the terms are oscillating, but the magnitudes go to 0, and this will converge to 0. Okay. Again, let's just connect this again to the continuous cases. So just as a follow-up, geometric sequences would be related to growth and decay functions. Okay, so you might recall the graph of y equals e to the x. E to the 0 is 1. We've got a horizontal asymptote here on the left, but unbounded growth on the right. So as x goes to infinity, e to the x goes to infinity. On the other hand, e to the opposite x is a decay function, and x goes to infinity, e to the opposite x goes to 0. Okay. Okay. And another way to write e to the opposite x would be 1 over e to the x. Okay. Just another example, y equals 2 to the x would have the same shape as the above growth function, and so would have unbounded growth as x goes to infinity. But 2 to the opposite x, which also could be written as 1/2 to the x, would be a decay function. And so 1/2 to the x goes to 0 as x goes to infinity. Okay. And you know you have a growth or a decay function depending on the base. So if we have a to the x, we're going to have a growth function if a is, when we usually let a be positive, if a is less than 1. We have a constant function if a equals 1, and we have a decay function if a, I have this backwards, don't I? This will be greater than, this will be less than. Okay. So I'll stop there, and we can look at some more examples in the next video. Thank you.